Hey guys.
Hey, Professor Chen, how you doing?
Good. How are you? What's up?
Doing good. Just, chilling at the house.
Nice. 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 All right, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing today?
Good, Professor. How you doing?
Good, good, good to hear. Yep, thanks for asking. All right, and so today we're just going to keep marching along, and so today we're going to finish up our lecture notes on the 1D blood flow equations, right? And so if you notice, from the last lecture, we're pivoting in this class a little bit, and so it was a little bit is quite intense of a math last time, and so today's not going to be any different, and so it's going to be some intense math today. And so, as we're going through, all these heavy derivations, I know it's kind of easy to kind of get lost in the details of the math. And so, unfortunately, in order to kind of draw a lot of the conclusions that we're going to make for this, for these units, we kind of have to go through the math. But I really want you guys to pay attention to not really to all the mathematical details, but kind of more just kind of big picture of how do these equations and how do these concepts, how do they relate to kind of what we understand from blood flow in general? Because at this point in the class, like you guys understand blood flow pretty well. Like before the spring break, we've gone over a lot of the essential qualities of blood flow, things like wave propagation, things like pressure waveforms, flow waveforms, things like resistance, compliance, things like that. And so you guys already understand a lot about blood flow. And so, the goal, so, the idea nowadays, with, among all these, complex modeling techniques is to take, what you already know about blood flow and say, what does this modeling technique, what does it do to help us, understand that or analyze that better, okay? And in particular, for these 1D equations, what I want you guys to focus on mainly is kind of the wave propagation phenomena, right? And so unfortunately, I think a lot of that stuff won't be very clear until we get to next week. And so next week we'll really see, how these 1D equations, how we can actually use them to analyze like wave propagation phenomena. But in terms of what I expect you to know and what I want you to get out of this, I'm not going to ask you to recreate any of these derivations in practice or even, to solve these PDEs. It's just that, the unfortunate thing with this is that we kind of have to go through all the details of the derivation to really kind of understand what this modeling methodology does for us, right? Because by the end of the class, we'll be going over a lot of different computational methods for modeling blood flow, right? And so we've already seen two already. So we've seen LPMs and we've seen CFD, right? And then by the end of this class, you'll have 1D equations. You'll also have Wormersley's, methods as well. And so, I want you to kind of take kind of a broad look at all these different methodologies. And I want you to be able to say, what does an LPMs do for me? What does 1D equations do for me? What does CFD do for me? Because, there's not one tool that kind of fits to every kind of situation, right? And so, it's kind of the same thing with other engineering as well, like for thermal engineering, for just general fluid mechanics, for structures, right? So there's not one tool that fits to every single situation. And blood flow is exactly the same thing too, right? And so part of being kind of an expert or kind of being an engineer in this topic is to understand, what's the best tool to use for these kinds of situations. And so that's what I kind of want you guys to kind of take away from this is that, for blood flow, there's lots of different tools that are available for us in order to simulate these things. But, the question is, what's the best tool or, what are the best tools to use for certain kinds of situations? Okay. Okay, so any questions I can answer before we get started for today? Okay. All right, so let's go ahead and continue on. And so we're going to continue on with the 1D equations for blood flow. Okay. And just to kind of refresh your memory, for the 1D equations, basically the way that we're going to obtain them is we're going to take our Navier-Stokes equations. And Navier-Stokes equations, remember, that consists of both conservation of mass and conservation of momentum. Okay. And so we're going to take both of those equations and we're going to integrate them across the cross-section. And so if you think of integrating as kind of a way to kind of, mathematically average, a certain quantity over a certain space, then essentially what we're doing is we're kind of averaging the Navier-Stokes equation across a cross-section of the vessel, right? Because normally you have a vessel that looks like this, right? And by averaging across the cross-section, what we're basically doing is we're kind of slicing the blood vessel, in kind of a way like this. So we're basically cutting it along, okay, to get a little like blood vessel pepperoni, I guess you can say, okay. And then we're going to average it across this cross-section, right? And so we kind of get like an area average, effect for the Navier-Stokes equations, right? And that makes our situation a little bit simpler than just solving Navier-Stokes straight up. Okay? And what we obtain from this, or what the goal is to basically put our equations in terms of two main unknowns. Okay? And so the first solution variable is going to be the flow rate, Q. Okay. And the other unknown is going to be the area, A. Okay. This is local cross-sectional area. Okay. A third unknown will be the pressure, but it's not directly solved for in the equation. We kind of do something else for the pressure that you'll see later. And so I'll do in parentheses 3 pressure. So pressure's there, and we do solve for it, but it's not a direct output from the PDEs. Okay. All right, and so last time, where we left off was we had finished integrating our conservation of mass equation, and we were in the middle of doing our integration on the conservation of momentum, right? And so I think we did about half of the terms because we had 6 different integrals that we had to do, and so we'll pick it up from integral 4. Okay. All right, so any questions on this so far? Okay, and so let's go ahead and pick it up. And then so we're going to be integrating momentum equation. All right. Okay, so we had six different integrals that we had to do, and so we did integrals 1 through 3 there. And so now let's start with integral 4. Okay. And so to kind of refresh your memory, integral 4 looks like the following. So we have 2 pi, integral from 0 to big R of 1 over rho, partial p partial z, r dr. Okay. And so this was our pressure gradient term, and we're just integrating it across the cross section. Okay. And for this term's actually pretty simple to compute, because what we're going to do is we're going to assume the pressure, or I should say the pressure gradient, does not depend on R. Okay. And so this is basically the same assumption as, we're assuming the pressure is uniform across the cross section. Right? And so what this will allow us to do is it'll allow us to take these terms and just pull them right out of the integral, right? Because if they don't depend on R, then there's nothing really to integrate, right? And so if we do that, we have 1 over rho partial p partial z times 2 pi integral from 0 to big R of r dr. Okay. these quantities right here, 2 pi times integral from 0 to big R of r dr, this is exactly the same as the area, the cross-sectional area of the vessel, right? And so let's go ahead and substitute A for that. And then we get the following expression for integral 4. And so integral 4 is just simply going to be A over rho, partial P, partial Z. Right, so nice and simple. So there's nothing that we need to do for this. Okay. All right, so that's integral 4, and so now let's do integral 5, right? And so integral 5 looks like the following. Okay, so we had 2 pi times integral from 0 to big R of nu.
Sir?
Yep.
Is that area over pressure or density?
It's density. Yep.
Okay. Thank you.
Right, so integral 5 is integral from 0 to big R of viscosity, nu, divided by little r, partial r of r, partial uz, partial r dr, okay? Right, and so from here we can just evaluate this integral because this r and this r is going to cancel out. And of course, nu here, our viscosity is a constant, and so we can just pull that out of the integral, okay? And so from this we get 2 pi r, or 2 pi nu times integral from 0 to big R of partial r of r partial uz partial r times dr, okay? These dRs are going to cancel out with each other. And then when we integrate, the integration is going to take care of this partial term up here, okay? And so what we get from this is 2 pi nu times r, big R, times partial uz, partial r, evaluated at r is equal to big R, okay? Right. And so at this point, we can't really do much with this one because we need to assume something for little uz, right? And so for this one, this is another one we're just gonna leave it as is for now. Right, and then we'll come back to it later once we once we finish with everything else. Okay. All right. So any questions on integrals 4 and 5 here? Okay. All right. So now we have integral 6, the last integral. Okay. And so integral 6 was 2 pi integral from 0 to big R of nu partial squared uz partial z squared r dr. Okay. And then we're going to do the same trick that we did kind of before with the conservation of mass, where we're going to take this second order derivative and just pop it out of the integral. Okay. And so we have and we'll pull the viscosity out of the integral too, right? And so we're going to have 2 pi nu times partial squared partial z squared of integral of uz r dr from 0 to big R. Okay. And then from here, what we can see is that we have a 2 pi here, and we have this integral right here. Okay. And these guys combine to make q, right? So remember, our q is defined as 2 pi integral from 0 to big R of uz r dr. And so that's exactly what we have here. Okay. And so we're going to go ahead and plug in q for that. And so we have integral 6. This is equal to viscosity nu times partial squared q partial z squared. Okay. Right. And so another nice and simple integral to compute. Okay. All right. And so now that we've evaluated all 6 of the integrals, we can go ahead and put it all together, into one equation, right? So it's almost like we've assembled the infinity stones, except this is not nearly as exciting or cool. All right, and so integral 1, remember that was just partial q, partial t, and so that's good. Next, we're going to combine integrals 2 and 3 because they have the same form, and so that's 2 pi partial z integral from 0 to big R of uz squared r dr. Okay, so let me go ahead and label these. And so this right here was integral 1. This right here is 2 plus 3. Okay, so that's what we did at the end of class last time. Right? And then to this, we're going to add integral 4, which we just computed, which was a over density times partial p partial z. Okay, so that was integral 4. Okay, and it's going to be equal to integrals 5 and 6. Right? And so integral 5 was 2 pi nu times r partial uz partial r. R is equal to big R. Okay, and so this was integral 5. And then we're going to add integral 6 to this. So it's nu partial squared q partial z squared. Okay. And this is integral 6. Okay. Okay. And so this is the form of the 1D equations that we have so far. Okay. So we still need to work on this a little bit because there's some terms that we have to get through still. But this is good progress here. And so, we've already simplified it quite a bit. There's just kind of a few more things that we have to do. Okay. Okay. So any questions on this so far? Okay. All right. So we've made good progress on these equations, but we're not through yet because remember what we want in the end is we want this equation to be just in terms of q and a. And so right now we have a lot of uninvited guests to the party that we don't want, right? And so in particular we have uz, okay, and so we got to do something about uz, and then we also have p, right? And so right now those are kind of the 2 terms that we want to eliminate, okay? And the way that we're going to do them is we're going to apply some additional assumptions and some additional equations to our model. So let's start with uz. Okay. The way that we're going to eliminate uz is that we have to assume we're going to have to assume the shape of the velocity profile. Okay. Okay. Or in other words, we're going to have to define, what uz of r looks like. Right. And thankfully, we actually already have a solution for this, right? And so you kind of think back to our review for fluids when we solved the Navier-Stokes equations and cylindrical coordinates. What we found was a solution for uz, and we found that it was a parabolic profile, right? And so let's use that same solution that we found previously, and then plug that into this expression here. Okay. All right. And so I'm going to go ahead and kind of write out some key results back from when we did our fluids review, and then we're going to use that in this equation here. Okay. Okay. And so this section is going to be the assumption of a parabolic velocity profile. Okay. And so what we're basically going to assume here is that uz of r is parabolic, right? And parabolic basically means that it's a quadratic function. Okay. Which is a reasonable assumption because we had already solved this problem before, and we already solved that it was parabolic. And so, it's not like we're making a big jump here. We're just using something that we've used before, right? And so in particular, we found that our velocity profile had the following expression. Okay? And so previously on EGME 442, right? We found that uz of r, this is equal to 1 over 4 mu dp dz, switch the thing midway, right? Partial p partial z times little r squared minus big R squared. Okay. And so this was the parabolic result that we got from basically just solving just a steady Navier-Stokes, right? So now, with these 1D equations, we have an unsteady situation, right? So our time derivative is not zero, but we can use the same result and assume that it looks basically the same, right? And that's a fairly reasonable assumption. Right? Another thing that we found was we found an expression for the flow rate, right? And so we actually took this velocity profile, we plugged it into that integral expression and evaluated that integral. And what we found was the volumetric flow rate of blood was equal to minus pi r to the 4th over 8 mu times partial p partial z. Right. And so all that we solved previously, right? And so this is really convenient here because for one, we have an expression for uz of r, and so that's something we can plug into the previous set of equations. But another thing is we have q here, right? And q is someone that's invited to the party, right? And so before actually we plug in for uz of r, let's take this expression for q, and let's see if we can incorporate it into this equation right here. Okay. And the way that we're going to do that is we notice that both uz and q have this partial p partial z, right? And in fact, the uz also has a 1 over 4 mu. And here we have almost that. So, we have 1 over 8 mu. And so let's use that quantity to solve, to plug in for that. Okay. All right, so let me go ahead and rewrite q here. And so first thing I'm going to do is I'm going to notice here that we have pi r to the 4th right here, right? And so let's go ahead and replace this with area, right? Because we know area is just pi r squared with a minus sign right here, okay? And so when we replace that, we have a minus a r squared divided by 8 mu partial p partial z, right? And so I just took 1 pi r squared and I turned that into area, and that's what I plugged in there, okay? And our pressure gradient is still the same. And then what I'm going to do now is I'm going to multiply this by 2 and divide by AR squared, okay? And so I'm going to multiply both sides by Q divided by AR squared, okay? And then what you get from that is 2Q over AR squared is equal to minus 1 over 4 mu partial p partial z. Okay. Right. And so this 1 over 4 mu times partial p partial z, this is exactly the same as what we have up here, right? And so let's plug in this 2q over ar squared with a minus sign, and then we can obtain uz of r in terms of q, right? In terms of q and a. And so that's that'll be kind of a little bit of a nicer expression for us to work with. Okay. All right. So any questions on this? Okay. And so we plug that expression in, then we get uz of r is equal to 2q all over ar squared times big R squared minus little r squared. And so now that we have uz of r in this case, in this form, let's go ahead and plug this into our integrals from the previous page. And so there's, in particular, there's two locations where we need to plug it in. And so we need to plug it in for the integral for 2 plus 3, right? And so integral 2 plus 3, that integral will look like the following. And so we have 2 pi partial z of integral from 0 to big R of uz squared r dr, right? And so that was just the integral that we had from before. And so let's take this uz and then plug it in for uz squared right here. Okay. All right, and the result for that is 2 pi partial z integral from 0 to r of 2q divided by ar squared times big R squared minus little r squared r dr. Okay. And so if we FOIL this guy out, then we get the following. Then we get 2 pi partial z integral from 0 to big R of 2q ar squared times big R to the 4th minus 2r squared plus little r to the 4th times r dr. Okay. Right. And so from here, what we can do is we can evaluate this integral because it's just a simple polynomial in r, right? Oops, squared. Knowing that this is a constant, and so we can kind of pull it out of the integral, right? And so what we get from this is, let me say, evaluate integral now. Okay. And so once we evaluate the integral, we have 8 pi divided by a squared times q squared over r to the 4th. Okay. Partial z of big R to the 6th divided by 2 minus 2r to the 6th divided by 2 or divided by 4 plus r to the 6th divided by 6. Okay. And then we add all those terms together and we combine them as one. And we end up with something that's fairly simple. Okay. And so all we end up with is partial z of 4q squared over 3a, and that's it. Right. Okay, and so we started with a fairly complex integral here, but once we assumed that the velocity profile was parabolic, and we plugged it in, and we do a painful amount of algebra and integrating, then we end up with something that's fairly simple. Right? It looks simple, but in reality, it's a little bit difficult to evaluate because because it's q squared and it's a q squared over 8, and so it's a very nonlinear term. But we'd be able to. This is a lot easier to do than those crazy integrals. Okay. Okay. So any questions on this? Okay. Oh, question. I'm in Spain without the S. Oh. It's a lot of math. So remember, it's the details of these derivations are not as important. And at the end of class, I'll show you basically a MATLAB implementation of this. But unfortunately, a big part of the 1D equations is just kind of knowing where they come from. And so, I think it's important to see it. I think it's not really important to really, really analyze every single detail of this derivation, but it's good to see where everything comes from and how everything kind of simplifies. But knowing every single detail is not the most important. At least to me, it's not the most important thing. Right? But we got to see it because it's part of what makes the 1D equations good. Right? Okay, and so that's integrals 2 plus 3, and so now let's evaluate integral 5 with this velocity profile. Okay, and so term 5 look like the following. So we have 2 pi times nu times r partial uz partial r. Okay, and we evaluate this at r is equal to big R. Right? And so let's go ahead and plug in our expression for uz into this. Right, and so we get 2 pi times nu times r times minus 2q divided by ar squared times 2r. Okay, and so a bunch of these r's are going to cancel out. Right, and so what we get from this is 2 times 2 times 2, which is 8, and so we end up with minus 8 pi nu q over a. Right. All right. And so finally, after all of that pain, we can finally express the 1D equations, okay, in their final form. Right? All right, and so the final form of the equations looks like the following. Right? And so we have partial q, partial t, okay, plus the first thing the first thing we just found, and so it's partial z times 4 over 3 q squared over a, right, plus a over rho partial p partial z, okay, is equal to minus 8 pi nu q over a, which is what we just found here, plus nu partial squared q partial z squared. Right? And so that's the momentum equation. Right? A lot of work to get here, but we got it, right? And then the other equation for the 1D equations is the continuity equation. The continuity equation was partial A partial T plus partial Q partial Z. And this right here is the mass equation. All right, so a lot of work to get here, but we got it, right? Takes me back to when we calculated air resistance and differential equations. Yeah, it was a beefy derivation, and so it took us about a lecture and a half to get here, but you guys did it, right? So we got to this point, and so we started with the Navier-Stokes equations, which everyone knows is very complicated and very scary, and we end up now with this equation, which it's still kind of complicated and kind of scary, but it is a little bit simpler to solve than the full Navier-Stokes. Okay. All right. But we're actually not quite done yet, and so there is one more thing that we have to talk about, and that's pressure, right? And so remember, because right now we have two equations, right? And so we have our momentum equation and we have our mass equation, and so just kind of in a linear kind of sense, what we can say is we can use these equations to solve for two unknowns, right? And so we can solve for flow and we can solve for area, right? But what we don't have is we don't have an equation to solve for pressure, right? And so we need one more equation to compute pressure. Right. And so, we need to add something to this, right? And the equation that we're going to add to this is a special kind of equation called a constitutive relationship. I always spell constitutive relationship wrong. Oops. And so a constitutive relation is a very special type of equation. And what it does is that it relates pressure to wall deformation, okay? And so in this case, we're going to have an equation that relates pressure and area. And it's going to be an algebraic equation. And so it's not a differential equation, thank goodness. But it's something that we need to have in order to complete this set of equations here, or to close the loop. Another way, that's another way to say it, okay? Right. So let me go write that down. So constitutive relationship is a mathematical relationship between pressure and wall deformation. Okay. And there's several options here. And so there's a couple of different types of equations that we can use, just because, different researchers have found different constitutive relationships, and all of these are valid. Okay. And so we'll go over two, just so that you can kind of see what they look like. And I'll point out which one is actually implemented in the code that we'll go over later. Okay. All right. So any questions on this? Okay. All right, so let's go over some constitutive relationships, right? And so the first relationship that we'll go over is the Cassava relationship. And his relationship looks like the following, right? So he says that P minus P0 is equal to EH0 divided by R0 times A over A0 minus 1. Okay. All right, so let's define some of these terms. Okay, so P0, this is the pressure in the reference state. Okay. E is the Young's modulus of the vessel wall. H0, this is the wall thickness. Okay. R0, this is the radius in the reference state. Okay. And A0, this is the cross-sectional area in the reference state. Okay. And so you see, I use the term here reference state quite a bit, right? It's a reference state, reference state, reference state, right? And so what the reference state is basically kind of it's kind of like a base case, right? And so under kind of like a mean condition, like say like you have a mean pressure and mean flow in your blood vessel, these define like what the pressure is, what the radius is, what the cross-sectional area is, okay? All right. And so that's the first constitutive relationship that we have. And so the next one is a very similar one, except it's slightly different. Right? And the unfortunate thing with these constitutive relationship is that they do the thing that annoys me the most about science is that they're named after the person that discovered them, right? Which I never understood why, because just by looking at this Cassava model or this Olson model, it's like, oh yeah, I know who Olson is. It's a very famous person. We have no idea who these people are or what they look like. And like now it just makes their equations even more difficult to remember, because like if you try to remember what's the Olson equation, you have no idea what that means, right? But we have to go by the name that everyone calls it by, just so that we kind of know what we're talking about. But I always hate it when scientists name stuff after themselves. All right, so the Olson equation, we have P minus P0 is equal to 4/3 EH0 divided by R0. Okay. And it's 1 minus square root of A naught over A. Okay. So very similar, to the to the Cassava equation, but it's slightly different. Okay. And all the symbols here basically mean the exact same things. Okay. All right. And so, these aren't the only two constitutive models out there, and so there's lots of other ones, but these are the two that I kind of see most commonly used, especially for the 1D equations. Okay, right. And so, these exact equations, you don't have to remember, and so you're not going to actually use these for anything. But I wrote them just to kind of highlight some general trends, right? And so you can see that both of these equations here have the Young's modulus in them, right? And so we can see that no matter what constitutive model that you have, it's going to depend strongly on the material stiffness of the vessel wall. Okay. Okay. And so it depends on the material properties. It also depends on the geometric properties, right? Okay. And so the way that you compute pressures and the way that you relate that to the wall deformation, that depends on, things like, the material stiffness of the wall, things like the geometry, how big the vessel is, how long the vessel is, right? Or I guess not how long, but, how wide it is and what the area is, right? Okay. And so, these are all things that are really important. Okay. And the other thing that these are used for, which we won't go through the math of this, but you can use these relationships along with the 1D equations to quantify the wave propagation speed. Okay. And so that derivation is in the PDF textbook that I have posted on Canvas, but but we won't go over it here, just because I think we've had enough math for 1 week. Right? Okay, so any questions on this before we jump into a MATLAB script that I've provided for you guys? Okay. All right, and so now I can say with confidence that we're done deriving the equations, right? And so at this point, if you combine these constitutive models together with this with these equations here, we have a complete set of equations that we can use to solve for flow and area and pressure in a blood vessel. Okay. The unfortunate thing about these is that they're so complicated still that it's still basically impossible to solve by hand. And so the way that we solve these is that we need a computational code to obtain these solutions. Okay. And so I'm not going to ask you guys to develop a code to do that because I think that's kind of beyond the scope of this class. But what I did was I did obtain a MATLAB script that provided kind of a simple solution for these 1D equations. Okay. And so if you see on the Canvas site, there's a zip folder where it says sample 1D blood flow code. Okay. And so that code right there is it's basically complete. And so there's nothing you have to change for it. But what it does is it'll solve the 1D equations for just a single artery. Okay. And in particular, the settings for this simulation were done for one of the carotid arteries, right? And so the carotid arteries, those are the arteries that basically lead up to your brain, right? And so like the length and the size of this vessel was set to match the carotid artery, okay? And so what we're going to do for the rest of the class is we're going to look. I'm going to show you basically how that script is implemented, and kind of and there's going to be some connection to what we went over with CFD kind of before the spring break, and I'll show you how to run it and how to interpret the results. Okay. Okay, and so if you want to follow along, you can go ahead and download that folder from the course website, and it's a whole folder of different files, and so all the different MATLAB scripts work together. But we're just going to focus on just one of the files. But if you haven't already, you can go ahead and download that zip file, kind of while I'm still a little bit talking here. Okay, and in particular, the file that we're going to look at is called carotid.m. Okay. Right. And so if you want to follow along and run the script yourself, actually you can run the script already because I've already kind of implemented it all for you, and so you can go ahead and run that. But I'll talk about the different parts of the code and basically how to interpret it from there. So funny story about this code. So I didn't write this code myself. So this was written by a friend of mine. And usually when someone writes their code, especially something that's something like this, it takes a while to write these kinds of codes, right? And the funny thing about this code is that this was actually lost for a while. And so I asked my friend for this code, and he said this was on an old hard drive of his that he had almost thrown away a couple of years ago. And so he had to basically put this hard drive, kind of resuscitate it and then retrieve the code from this. So it was kind of like a 2-week process to obtain this code. So it was quite a journey, but he owes me one. And so, I kind of reminded him that when we were in grad school, there was one time where he called me at 9 a.m. on a Saturday morning to help me with the research problem of his. And at that point, I didn't really know him that well. And so I was more confused about how he obtained my phone number, and why is this person calling me at 9 a.m. in the morning? But I helped him, and I said, you owe me one for that time you called me at 9 a.m. So I made him resuscitate his hard drive and retrieve this code for us because I knew he had this because I remember he told me about it a long time ago. And so we can thank my friend for this. So because it did take him a while to revive his hard drive for this.
Professor.
Okay. Yep.
Which code are we opening?
It's the whole folder is called carotid.zip, And so if you open up that, if you unzip that folder, there's several different MATLAB files in there. And so there should be one called carotid.m. And so you can go ahead and just double click that file and open it up in MATLAB.
Just that one?
Just that one, yeah.
Okay.
Yeah. So that file is going to call some of the functions in some of the other files, but the other files we're not going to worry about that. And so we're just going to worry about carotid.m. Yeah. Okay. And so the situation that we're going to solve is going to look like this, right? And so we have we have our 1D solver code, and we're going to use it to simulate the flow and pressure in the following vessel. And so it's a 1D code, and so we're just going to have a one-dimensional vessel, right? So it's going to look like this. Okay. At the inlet to this vessel, let me draw it like this. Give myself a little bit more room. Okay. In the inlet to this vessel, we're going to prescribe a flow rate, and we're also going to prescribe the inlet area, right? And so we can say that this is the inlet of the vessel. This is the outlet. And then at the outside of the outlet, we're going to have an RCR boundary condition. Right? So you can think of it as an LPM that's going to be used as kind of a boundary condition for this model. Right? Okay. And then inside the model right here, we're going to have all the different properties. And so we're going to have the viscosity, we have the density, we have the radius, we have the Young's modulus, and we have the thickness. Okay. And of course, we have the length for this vessel as well. Okay. All right, and so we're gonna specify a flow at the inlet of this model, and it's going to be time dependent, and so it's not going to be steady. And then we're going to solve for the waveforms for flow and pressure, throughout this vessel. Okay. And so let me draw out the inflow waveform just so that you can kind of look at it. Right? And so this is part of the reason why we have so many files in this folder is because we needed to find the flow waveform for this. Right? Okay, so the flow waveform is going to be given in milliliters per second. Okay, and so that's on the y-axis, and on the x-axis we have time. Okay, and so the flow waveform looks like this, and this was actually taken from some measurements, and so this, I think they actually measured the flow in someone's carotid artery, and this is the waveform that results. It looks kind of flat for a while, and it goes up, and it has kind of a blip, and then it goes down just like that. Okay. Right, and so this is actually stored in one of the text files in there. And so if you open up inflow.txt or inflow.dat, then this is what it looks like. So you don't have to do that, but if you open up that file and copy and paste that into Excel, this is basically what you would see. Okay. Right, and what this simulation is going to do is it's going to simulate 6 different cycles of this waveform. Okay. And so basically this waveform is going to repeat itself 6 times, right? And so the reason we do this 6 times is because whenever you do an unsteady simulation like this, where your inlet condition is oscillating, you need to kind of run it for several cycles because it takes a couple cycles for the simulation to kind of warm up. That's kind of like what I like to think about it, right? And so actually for your final projects too, if you want to do an unsteady simulation with the pulse without inflow, I would probably ask you guys to do the same thing, where I would ask you to run it for several cycles in order for the conditions to kind of ramp up. Okay, so this is pretty standard for CFD stuff, is to kind of run unsteady simulations for several cycles just to make sure that you've kind of achieved kind of steady state. Okay. So any questions on this so far? All right. And so even though, these are the 1D equations, we have to treat this like we're running a, a computational, simulation, right? And just like we did with Vascular, we have to mesh our domain. Okay? Right? And so for a 1D domain, our 1D domain is just simply a line. And the way that we mesh a line is that we break it up into a bunch of smaller lines. Right? Right? And so instead of just having one big line segment here, we're going to break it up into lots of smaller line segments. Okay. And what you'll see from the code is that there's a way that we can control how fine our mesh is, right? And so inside the code, there's a parameter called N1. Okay. And so what this parameter does is it defines how many elements that we want to have in the mesh. Okay. Right. And so if we increase this number, that increases the amount of elements that we have. And if we decrease it, that decreases the amount of elements that we have, right? And so the more elements that we have, the more accurate the simulation is going to be, but it's also going to be more expensive, right? And so basically, everything that you understand about meshes from CFD, you can apply that here, except this is on a much smaller scale because it's just a 1D simulation. And so I think in the default settings, the amount of elements N1 should be 50. And so that should be plenty for this simulation. But you can of course, modify that and change it, if you want to see what's going on. Okay. And so another thing that we have to set here is, if you remember from CFD, is we have to set the time parameters. Okay. And so in particular, we have to set dt, which is the time step size. Right. And so remember, if you remember our analogy for a video in like frames per second, dt determines how much time there is in between frames. Right? And so the smaller the value for dt, the more accurate our simulation is. Okay. And then another thing we have to set is the total number of time steps. Right? Okay. And you'll see that we'll set both of these guys in the code. Okay. All right. All right. And so that's everything that I wanted to go over on the paper. At least in terms of theory, just connecting this back to CFD. But one thing I want you guys to keep in mind as we're running the simulation is that, remember, the 1D equations here, their best feature is that they assume that the walls are deformable. Right? That's by far the best feature of these 1D equations, is that the deformable walls kind of are just naturally just baked into the equations themselves, right? And so what this tells us is that, running the simulation, we should be able to observe some of the effects of pressure wave propagation. Okay? All right. And so I want you guys to look out for that, as we look at the results, and I'll highlight, the pressure wave propagation stuff as well. Okay. Okay. And so with that, let me go ahead and share my laptop screen. Okay. And let's start to look at the code. Okay. All right. And so if you're following along, you should see the code. So this is carotid.m. Okay. And you can see here that, we have to specify these parameters, right? And so the first parameter that we set here is n per. And so n per is set to 6, right? And so this is the number of heart cycles that we want to simulate. And so just like I mentioned before, since this is an unsteady simulation, we want to simulate multiple cycles. And this is, this is the amount of time, the amount of cycles that we're going to simulate. All right. And so next thing that we have to specify here is per t. And so what this parameter does is this specifies the length of each heart cycle in seconds, right? And so this is basically the amount of time it takes for one heartbeat. And so this is basically set to 1.1, which matches up with the inlet data that we have. Okay. Right. And so next thing we have to do is set the total amount of time. And so the total time is the just the product of these two, right? And so in total, we're going to simulate 6.6 seconds of simulation time, because that's just be 1.1 seconds per cycle for 6 cycles. And so that's 6.6 seconds overall. And then finally, we set the time step size to be 0.1 milliseconds. Okay. And so that's pretty small, but it's set to that, just so that, we get an accurate solution, because these 1D equations, they run very quickly anyway. And so, we can kind of, take this down quite a bit just to make sure we get an accurate solution. Okay. All right. And so here we can see we have the parameter n1. And so this is the number of finite elements that we want to divide our solution into. Okay. And so we have 50, and that should be perfectly fine for this, for this case. Right. Okay. And so from here, you don't have to, you don't really have to read any of this code. And so this is, we're basically just reading the inflow data. And so we're basically taking the, this inflow.dat right here. That was a mistake to open up in MATLAB, right? And so you can see here, this is the time series data for the inflow, right? And so it's fairly large, right? And so here we're just using MATLAB functions to load that in, and then just putting it in a format that we can use for the simulation. Okay. All right. And so the section that I really want you guys to pay attention to here is section 2, right? And or this I guess this is section 3 right here. And so section 3, this is where we're going to define all the properties for the simulation, right? And so we have to define things like the viscosity, the density, the reference pressure, the radius of the vessel, the length of the vessel, right? So, all of these are things that we have to specify. In particular, I want you to see the settings for the radius and the length. And so these are set to match, the same parameters as like a carotid artery. And so a carotid artery typically has a radius of about, 0.265 centimeters. And the length of the carotid artery is about 12.6 centimeters in length, right? And so these are kind of population average values for these guys. Okay? And then down here, what we have is the Young's modulus. And so this is the material stiffness of the vessel wall. And so we're using a fairly, conservative value of 7 times 10 to the 6 dyne per centimeter square. And I think that's the same thing as 0.7 megapascal. Right? And so that's a pretty, it doesn't work for every vessel, but for vessels that are close to the aorta, that's a pretty good value for the Young's modulus. Right? And we also have to specify the thickness of the vessel wall as well. Right? And so for these vessels, the thickness is 0.03 centimeters. Okay. All right. And so everything else here, you're welcome to read through the code. I actually did spend, half a day going through and commenting these to explain everything that's going on, because the code that my friend sent me had 0 comments. And so it actually took me half a day to kind of figure out what was going on. And so, you're definitely free to read this and see what's going on. But let's go ahead and run it and see what happens. And so you can see, after we click run, it does take a bit of time. And so it's not as fast as LPMs, but, we're able to obtain our results in a matter of seconds. Okay. Okay. And so let's look at these 2 results, and let's kind of analyze, what they look like. Right. And so you can see here, it should pop up 2 different figures. And so figure 1 should be, flow waveforms, and figure 2 should be pressure waveforms. Right. And so on these, you can see that there should be two lines here. And so in the blue, you can see I have the flow waveform at the inlet. And in the red, I have the flow waveform at the outlet, right? So that's basically at the two extremes of the vessels, right? And so at the very inlet and at the very outlet. And you can see here, I have the same thing for the pressure, okay? Right, and so you can see that these curves are different, right? And so if we measure the flow waveforms or we measure the pressure waveforms at different locations on the vessel, they look different. And this is a direct result of wave propagation, right? And so remember, the whole thing with wave propagation is that it changes, how the flow and pressure waveforms, they show up at different locations in the vessel wall, right? And so if the walls were rigid here, these would actually look identical. And because because if the walls are rigid, then the flow has to be the same everywhere and the pressure has to be the same everywhere. And so the fact that we have deformable walls here allows these curves to be different. Right? And so let's look at the pressure waveform first, right? Because I think that one's a little bit easier to parse. And so in particular, the area that I want you guys to focus on is kind of this area right here in the beginning. Right? And so you can see here that, the inlet waveform comes down and it starts to go up right here. And the outlet waveform does the same thing, except it's a little bit delayed, right? And so you can see compared to the inlet waveform, the outlet waveform kind of ramps up a little bit after the inlet, right? And this is one of the primary effects that we talked about in terms of wave propagation, right? And so in terms of wave propagation, we know that further down the vascular tree, as you get farther away from the heart, the pressure waveforms tend to be delayed a little bit, right? So there's this little bit of phase lag that occurs, for the downstream vessels as a direct result of wave propagation, right? And so you can see that effect is taking place here. And so for the outlet, you can see the pressure waveform is slightly delayed, because of the wall deformation and because of the pressure wave propagation, okay? And so that's pretty cool. And so, from this 1D simulation, we're able to get this, very realistic, effect, that we wouldn't have gotten otherwise without it. Okay. All right. And so let's look at the flow waveforms now. Right. And so the inlet flow waveform, what you can see in blue, this is directly what we're specifying in the simulation, right? And so we're directly feeding this in. And for the outlet one, you can see that the curve is kind of depressed a little bit, right? And so you can see, obviously, the peak is lower, but, in the regions where, the inlet is low, the outlet waveform is a little bit higher, right? And so you can see that, the waveform compared to the inlet is like kind of squished a little bit, right? And this is again a direct result of the wall deformation, right? Because what did we say before about, for flexible walls? If the walls are flexible, what can happen is that they can temporarily store flow. And then, once the heart is relaxing, then it can eject that flow, right? And so that's what you see here. And so, during the filling phase or during the times when the flow is high, what's happening is that, the difference in between these waveforms here, that's being stored within the vessel, because that vessel is literally stretching out in order to kind of store that flow, right? And so that's why you see that the outlet peak is not as high. But when the inlet flow goes down, what's happening then is that, the vessels are deflating, right? And so all that flow that it had stored from before, it's now kind of squeezing and kind of letting that flow out. And so you have kind of a, a higher flow here in diastole when the inlet flow waveform is relaxing, right? And so again, this is a direct result of the wall deformation, where we have flow storage, and then over here we have flow ejection, right? And then over here, you have a little bit of phase lag too. And so kind of the same thing with this pressure waveform, because of that wave propagation. And so, this is kind of just a simple example because it's just one vessel, right? But even in just this one vessel, and due to the 1D equations, we see these really cool, realistic effects, that we can't see, we wouldn't be able to get this in LPMs. And with CFD, if you're using rigid walls, you won't be able to see this either, right? And so these are things that are, just come very naturally for the 1D equations, and we obtain these simulation results in 6.5 seconds, which is, it's not immediate, but it's also, doesn't take forever too, right? So, for those of you who've already run your CFD simulations, you can see that, if you try running it on your computer, it's going to take you, maybe an hour or two. And if you run on the cluster, that requires, dozens and dozens of processors. But here, just on your, just on your personal computer on just one processor, you're able to obtain results in 6.5 seconds, which is really nice. Okay. All right. So any questions on this? Okay. Right. And so this code is yours to keep. And so, you can thank my friend for it. And so, part of your homework is I want you to kind of play around with these values a little bit and see how they affect the results, right? And so you can modify the radius, you can modify the length, you can modify the stiffness, just kind of, just modify and just kind of play around with it and see what happens. Right? And the beautiful thing about simulations is that you can do something crazy. So let's say that we have a, like a giraffe or something. And so we'll make this vessel, 100 centimeters long instead, right? And we can simulate it and we can see what happens, right? Okay. And you can see that, if you make the vessel a lot longer, then you have, really crazy results, right? And so, don't be afraid. So go ahead and change stuff. It's just a computer program. And so, we're not actually hurting anyone through this. So, you can go ahead and go wild with this, right? So let me just double check real quick that I got everything. Yep. All right. So that's all I got planned for today. And so, have fun with this code, definitely play around with it. If you want to see how the 1D equations are implemented, you're definitely free to, explore some of these other files. And you'll see that, that you'll see elements of the equations that we went over in class. So definitely, check that out if you want to, right? And so with that, that's all I got. So thank you guys for tuning in today. Hope you guys have a great weekend, and I'll see you guys on Tuesday. Thanks, guys. Take care. Great. Stephen, did you have any other questions?
No, I'm good. I have a question about the project.
Okay. Yeah. What's up?
So how do we choosing the project? Like,
You mean how do you choose a model?
yeah, and we just email it to you, right?
Yeah. So if you you can go ahead and choose one. And so you know where the website to go to, right? And so you go to the repository website and just and you can browse just the available models that's there. And just whichever one looks the most interesting to you, or the one that you want to do, just send me the there's like an ID number for it, and so it's like OSMSC something and a number, and so just send me that number, and then I'll send you the files for the project.
Okay, I see. Thank you.
Yep. Mm-hmm.